Hello everyone, this is Joe from RIT. I'm here to present our journal first paper, Improving Vulnerability Inspection Efficiency Using Active Learning. This paper was accepted at the TSE journal. As most of us have already known, software security vulnerabilities have heavy impact, and here are two of such examples. However, these vulnerabilities are very rare, as reviewed in this graph by Dr. Zimmerman. The vulnerable modules colored in red are extremely rare in the Mozilla Firefox codebase. And this caused a problem that when we try to use machine learning algorithms to predict for such software vulnerabilities, we reach either very low precision or very low recall. Therefore, although machine learning algorithm has low cost, basically no human effort involved, but they have very low accuracy as well. So it is not reliable. That is why for the current practice, for mission-critical software systems, we still use engineers to manually inspect the entire code base looking for vulnerabilities before releases. And this practice, although has high accuracy, but it also costs a lot, much more. So in this work, we want to combine the advantages of both machine learning and humans to build a human-in-the-loop system that have both high accuracy and low human cost. So the idea is to treat this problem as an information retrieval problem, which is how to find very rare vulnerable files inside the code base. If we input the code base under inspection to a machine learning algorithm, and the algorithm then suggests some of the files for the humans to inspect. The humans then inspect the files and tell the machine learning algorithm that which files are vulnerable and which are not. Then the algorithm can utilize this human oracle feedback to update or retrain their model so that they can make better suggestions on what files has higher probability of being vulnerable. And these files will be inspected by humans next. Here is a brief overview of our proposed framework. It consists of three parts. The first part focuses on how do we find more vulnerabilities with less human effort. And the second part focuses on the stopping rule. Say, for example, if a human has already inspected some of the files and found 50 software vulnerabilities, and if we can estimate the number of vulnerabilities left in the uninspected code base, say, for example, the number is 3, then we can tell the human that it is a good time to stop here because we have already reached a higher than 90% recall, and the cost to find those 3 vulnerabilities left is probably too high. And the third part is about human error corrections. According to existing literatures, humans in average have a chance of close to 50% to miss the vulnerabilities when they inspect source code files. This is why it is also necessary to double-check and correct these human errors. As for performance, we simulate our approach along with some other baseline approaches on Mozilla Firefox dataset. In the first simulation, we assume human has perfect precision and recall. And in this case, if we have a human to inspect 100% of the code, then we can find 100% of the vulnerabilities. On the other hand, if we apply some machine learning algorithms to train on part of the code with oracles provided and test on the rest, for the testing part, we can reach 83% recall by asking human to inspect 15% of the code. And for our algorithm, we apply a machine learning algorithm with humans, and we can reach 85% recall by asking human to inspect 13% of the code, or reach 95% recall by inspecting 20% of the code. Note that our approach does not require any training data in the beginning, and the cost calculated here also considers the human effort required to label the source code files which provided for the machine learning algorithm to train itself. On the other hand, the cost values here for this baseline approaches does not consider the cost for the training data. So this cost should be higher. And in our second simulation, we assume that the human has a 50% recall. And in that case, if one human inspect all the code, we can reach 50% recall. And if two humans inspect all the codes, which incurs 200% of cost, then 75% recall can be reached. In our approach, a machine learning algorithm with two humans, and one reviewing inspecting the code, and the others inspecting only the suspicious file that the machine learning algorithm disagree with the first human's decisions. Then we can reach 70% recall with only 30% cost. And if we increase one humans, then we can reach 81% recall by increasing 10% cost. So the takeaway message here is that we believe and we show that human plus machine works better than human alone or machine alone in accomplishing some of the tasks. Thank you.